Let's do another symmetry problem. Symmetry and intercepts problem. So I have f of x is equal to x cubed minus x, which I could also look at it as y equals x cubed minus x. I do prefer the f of x notation. It's letting me know that what I have here is a function of x. So x is going to be my input value, and y, or f of x, is going to be my output value. So first, I need to find the y-intercept. Now I put it up here in the board. It's hiding behind the recorder thing. Let's move that. Okay. I want to find the y-intercept. And when I make a little graph, every time I would intercept the y-axis, my x value is going to be 0. So if I want to find a y-intercept, I just set x equal to 0. Well, that's the easy one to do. So y equals 0 cubed minus 0. So my y-intercept is 0. And if I can put that up here as 0, or probably better is to put it as an ordered pair. So it's x is 0 and y is 0. So I would have the ordered pair 0, 0. So we'll do it there as an ordered pair. That's my y-intercept here. Let's find my x-intercept. Well, for the x-intercept, I'm going to set y equal to 0. So I'm going to go, make a different color. I'm going to go 0 is equal to x cubed minus x. So what I need to find, I'm looking for my x-intercepts. And I can have multiple x-intercepts. So again, if I made a little graph, every place I intercept the x-axis is a y equals 0. We call them zeros. Sometimes we call them solutions. Sometimes they're called roots. Sometimes they're called x-intercepts. And sometimes they're called factors. All of those are related to the exact same thing as where a graph is crossing the x-axis. So, let's look at this problem right here. Here I have to use a little bit of algebra. So, I'm going to switch sides here. I'm going to go x cubed minus x. So I like my x's on the left side. I had a little interruption there. So I'm going to go x cubed minus x is equal to 0. You know what? I actually don't like them on the left side. It doesn't matter. Doesn't matter. So my algebra here is going to be this. I'm going to, whenever I have a polynomial, and we will learn this later on as well, the first thing I should do to simplify it is to see if there are any common terms in both the terms. If there are any common factors of both the terms, and there is. There is x. So I have x times x squared minus 1 equals 0. Well, part of that becomes immediately clear. If x is equal to 0, then this whole thing is going to be equal to 0, and it's going to be equal to 0. So that's one of my x-intercepts. It's going to be, I'm going to make it in set notation here, is going to be 0. But I also have this portion of my expression here, which I have factored, and I can do something with that. Well, I can see right there that that is the difference of two perfect squares. I know the difference of two perfect squares is going to wind up to be, in this case, x plus 1, x minus 1 equals 0. So in order for this piece right here to be equal to 0, x can be minus 1. And in order for this piece over here to be equal to 0, x can be positive 1. Now another way that I could have done that is I could have said, you can see here I have x squared minus 1 equals 0. And since I don't have any middle term of x in here, so I don't have, I don't have x squared plus 3x minus 1. There is no middle term with just a single power. All I have are the two terms that are the squared term and the constant. I can also change that. I can add 1 to both sides. That would give me x squared is equal to 1. And then I can take the square root of both sides. And if I do that, I will get x is equal to plus or minus 1, which is exactly what I have right here. So I have 3 roots, 3 zeros, 3 x-intercepts for this equation, and I have them as the set, and I'm going to write them a little bit better here. It's the set of 0, 1, and -1. Or I could have written it as 3 ordered pairs. That would be 0, 0, 1, 0, and -1, 0. Now, I want to point something out here, because it is not uncommon for people to kind of forget their algebra a little bit, and once they solve this and they find out that 0 works, they just stop right there. And they forget about either factoring this, or they don't know how to proceed. So this is where you really want to double check your work with your calculator. So I have, I'm going to go to my calculator here. Let's go second quick. I'm going to go y equals. I'm going to clear that expression. I'm going to put in my equation. I want to graph my equation because I'm looking for the zeros. I'm looking for the x-intercepts. So I can go x cubed minus x. And I'm going to go zoom 6. Well, it's a little bit kind of tight there, but it even kind of looks to me as if I have 3 intercepts. I'm not quite positive, but I think I have 3 intercepts. And if I really want to see it more closely, well, I can kind of change my window size. So I'm going to go window, and I'm going to make it, I'm going to use 4. I like 4 a lot of times. It seems to work. So -4 and 4. I'll leave my scale at 1, and I'll make my y scale different too. I'll also do that -4 and 4. So I'm expanding my graph, and now I'm going to push graph. And sure enough, now I can see very clearly that I have 3 intercepts. I can even see where they are. I could solve for them on the calculator, but it's letting me know, hey, wait a minute, you didn't do all the work. There's still a couple more intercepts that we need to find here. So use your calculator. I usually have the honesty checkbox. If you use your calculator and it helps you get the answer right, great. You'll mark the checkbox, so you'll get a little bit off, but you won't lose the whole problem. So now I found my intercepts, and I'm going to go on to symmetry. So x-axis symmetry, I'll start with that, and that is where I'm changing my y's to -y. Okay, so here's my original equation. So I'm going to make it -y equals x cubed minus x. Well, my original equation here, let's make it all in terms of y by multiplying both sides by -1. So I get y equals negative x cubed plus x. And I don't know, this is clearly not the same as that. So I do not have x-axis symmetry. Let's write it over here. No. How about y-axis symmetry? Well, y-axis symmetry is where, for every time I have an xy, my x's can be negative. Well, I can test that out too. Well, let's erase the -y here. Thank you. Okay. So I have y equals parentheses. Use parentheses. It will help keep it clear. Negative x cubed minus negative x. Yes, you could probably do this one in your head, but it's much better to use parentheses. It just helps it stay clear. So I have y is equal to, now I know negative x cubed is in fact equal to negative x cubed plus x. Well, is this y equal to this y. No, I don't think those are equal. I don't think they're equal at all. So, no, I do not have symmetry over the y-axis. How about the origin? Well, the origin is where I'm going to change both my x and my y to be negative. Let's see what that looks like. You know what? I can erase this here so we can see it more clearly. Okay, here's my original equation. I'm going to change both my y and my x. Negative y equals, parentheses, negative x cubed minus negative x. So my y is negative and my x's are negative. Well, let's simplify it a little bit. Negative y equals negative x cubed plus x. And I want to compare it with this guy right here, so it's easiest just to make my y's positive. So in order to make my y positive here, I'm going to multiply this by negative 1. Now if I multiply that by negative 1, I have to multiply the other side by negative 1. So this is going to be y equals, well, negative 1 times negative x cubed would be positive x cubed. And negative 1 times x would be minus x. And look at my y equals right here. And it looks exactly like my original. So yes, I do have symmetry over the origin. And if we go back for a second to our graph, you can see the graph, it looks like we have symmetry over the origin. I mean, it's not nice and clean like just the regular graph of x cubed, but you can see that if I flip this first over the x-axis and then over the y-axis, first over the y-axis and then over the x-axis, they would line up perfectly. So that is what something that's symmetrical over the origin looks like.